Okay, so this week we've been looking at water hardness, and what we're going to need to do today is a titration to find the total water hardness in a sample of the water using EDTA in our burette. So just a little bit of theory just to kind of back us up as we're starting this. So just to start us off, water hardness, remember, is caused by calcium 2+ and magnesium 2+ ions dissolved in the water. And when they're dissolved in the water, the more there is, the harder the water, and we want to find out the concentration of the calcium 2+ and magnesium 2+ ions. Now when we get to the equation later on, we're not going to see them as Ca2+ and Mg2+. We're going to simplify that down and we're just going to call them M2+. So metal ions with the +2 charge, just to include both of them. We're going to be using a chemical called EDTA, and that's new to us. And EDTA has a really long name that unfortunately you do need to know. And that name is, and it has to be spelled right as well, it's ethylene diamine tetraacetic, already making a mistake, tetraacetic acid. So ethylene diamine tetraacetic acid. Now for me to learn that off, I break that up into separate words. So in my head, I'm taking the ethylene separately, then the diamine, then the tetraacetic, and the acid. But this is the only space in the word. This part is all one word long. Ethylene diamine tetraacetic acid. Now to use this chemical, there are certain conditions that we need. Well, one main condition, and we need it to have a pH of 10. So whatever solution it's in, it needs to be at pH 10, and that's because our indicator won't work otherwise. The indicator that we're going to use only works at a pH of 10. And to get a pH of 10, we're going to use a pH 10 buffer. So we're going to add about 1 ml of pH 10 buffer each time we do this titration. And the indicator we're going to use, I never added that in, so our indicator is going to be called Eriochrome black tea. Eriochrome black tea. And it's slightly different to other indicators that we've looked at up till now, because instead of adding a liquid indicator, we're actually going to be adding a small amount of the solid indicator. So some of the powder itself we're going to be adding to the conical flask, but we'll see that as we get to the experiment. The equation in this case, just so that we know our ratio for later on, we have our M2+ ions, they're our calcium and our magnesium. Those M2+ ions will react with this stuff. Now this is a simplified way of writing EDTA. So this is my EDTA that's coming from my burette. And that EDTA will react with the metal 2+ ions to form this EDTA complex. Okay, and we're not too concerned about this complex. What we mean by complex isn't that it's complicated. We just basically mean that when we have our calcium or our magnesium ion, so let's say that's your calcium or your magnesium ion in the water, the complex is like this big molecule. The EDTA is a huge long molecule, and a really simplified structure would be something like this, okay? Now that's just overly simplified, but it can bend and it can wrap itself around the calcium or the magnesium ion, and when it wraps around, it can form 4 different binding sites with it. It can bind with it in 4 different places at the same time. So it's like it's giving it a big hug basically, and it's hugging right around the calcium and the magnesium, and now it's no longer part of the water. It's no longer contributing to the water hardness. When we have something like this wrapping around a molecule, that's what we call a complex. And that's why this titration isn't known as an acid-base titration or a redox titration. This one is a complexometric titration. Okay, so complexometric titration. And that's because it forms this complex around the calcium and magnesium ions to remove it. So back to the equation here. we have our calcium and magnesium ions reacting with our EDTA. It forms a complex and 2 H pluses. When we get to our calculations, all we're concerned about is the concentrations and the amounts of the metal ions and the EDTA. And if we want our ratio, we just need to look at the numbers in front. So the number in front of the M2 plus is a 1. The number in 2 plus, the number in front of my EDTA is also a 1. So it's a 1:1 ratio. So it'll make our calculations nice and handy. Okay, so the water we're going to be using is just regular bottled water, and it's quite high in calcium and magnesium, and it actually has the concentrations written on the back, so I'll be able to compare the values when I'm done to see how accurate I was. Now, I'm going to have to rinse my pipette with deionized water and then with my water sample, but I don't want to contaminate my water sample by putting the pipette directly into the bottle. So I just have a beaker here that I'm after putting some of the water into from the bottle. So I'm going to rinse my pipette now with some deionized water and my water sample. Okay, now that I've rinsed the pipette out with deionized water and the water sample, what I'm going to need to do is transfer some of the water sample into my conical flask for my titration. Now, because the calcium and magnesium levels they're high in bottled water compared to other water, but they're still quite low overall, 25 mils is not going to be enough. So I'm going to have to pipette 100 mils of the water sample into the conical flask to ensure that there's enough calcium and magnesium ions in there for the EDTA to actually react with and get a proper burette reading from. So to do that, I'm going to use the pipette 4 times. And after I've used that 4 times, I'm just going to use a dropper, which has a 1 milliliter mark on the side. Not focusing, never mind, it does anyway. And I'm going to use that to add 1 ml of my buffer solution into my conical flask. Okay, so now I have my 100 mils of my water sample and 1 milliliter of my pH buffer 10 in the conical flask. Next, what I need to do is add my indicator. Now, as I said, we were going to add the indicator at the solid indicator, not dissolved as a liquid. So I'm just going to scoop up some of this Chrome black tea, just so we can have a look at it. And you can see that it's a fine black powder. So its appearance is a black powder. And I only want the tiniest amount. So I'm actually going to empty the spatula tip so there's only a little bit stuck to it. I'm just going to give it a little tap on the conical flask, just so the smallest amount goes in. And when the smallest amount goes in, I can swirl it. And it turns out I might have added maybe a little bit too small of an amount. There's a little bit more. And if I just put that under a white tile, we'll see that it's a nice wine red colour. Now, in reality it's purple, but as far as the leaf insert is concerned and the marking scheme is concerned, that is a wine red. And now we can go on to preparing our burette for the titration. Now, to prepare the burette, what I'm going to have to do is rinse it first with deionized water, as usual, and then I'm going to rinse it with my EDTA solution. Now, I've made this EDTA solution freshly just today in a glass volumetric flask. Normally, we wouldn't store this in glass because the EDTA reacts with the sodium ions in the glass and can break the glass down. So it's not very good for the glass vessel if we store it in there. So normally we store it in plastic, but because I've made it up fresh and I'm going to use it straight away, it doesn't matter too much because it's not going to be in there for any long amount of time. So I'm going to go now and rinse my burette with my deionized water and my EDTA solution. And then I'm going to clamp my burette vertically in the clamp here. Okay, so the burette has been rinsed with deionized water and it's been rinsed with the EDTA solution. So now I'm going to take the EDTA solution and using a funnel, I'm going to fill it to above the 0 mark. So I'm going to be careful not to overfill the burette. Okay, a little bit more. So we have the burette filled. And now what I need to do is to empty it into waste to fill the part below the tap and to ensure that the bottom of the meniscus is on the 0 mark. So let's see how we can do this on camera. So at eye level, open the tap to get the meniscus onto the 0 level. the 0 mark at eye level, and can we see that? Pretty much there, yeah, okay. And make sure you're emptying that into a waste beaker. You're not emptying it back into your EDTA bottle, your volumetric flask. Basically ready to get going with the titration. Do not forget to remove the funnel from the top of the burette. And remember, we're starting with this wine red colour. Now, it has actually developed darker since we've left it. It's kind of a purplish, but we call it wine red. And the colour change we're looking for is, we're starting with this wine red and we're going to go until it's blue. Because when the EDTA has removed all of the calcium and magnesium from the water, it will turn to a blue colour. But this colour change isn't as instant as with other indicators, so we need to make sure that we're taking this slowly. So we're going to try and do this one-handed. So I'm going to be adding, then swirling, adding, then swirling, but you know as you do it, you would be doing this all in one go. And with this titration, it shouldn't take a really big amount. It should be gone within, I don't know, 5 to 10 mils of EDTA solution. That's blue. So that's already gone for me, okay? Now that's my rough titration, and it's gone at around, trying to get this to focus now. At around 3.1 millilitres. So it goes quite soon, and I've probably even overshot that. So we need to do 2 more accurate ones. Now, I'm not going to film the 2 more accurate ones. We know what we need to do. We need to take the conical flask, rinse it out in the sink with deionized water, and we need to refill everything. So another 100 mils of your water, another 1 mil of your buffer, and a very, very small sprinkle of your area chrome black tea indicator. What I should have done as well during that titration, but I didn't really have enough time, was use my wash bottle to wash down the sides to make sure that all of the EDTA gets mixed in. Now, when we're doing that, it's okay to use deionized water, but not tap water. And that's because if I add tap water, I'm adding more calcium and magnesium ions. Whereas if I only use deionized water, all of the ions have been removed. I'm not adding any more calcium and magnesium, so I'm not going to affect my result. Okay, so now we're going to start the calculations now to try to find the concentration of the calcium and magnesium ions in the water, the total water hardness. So what we always start off with is the concentration that we know. And if you look back at the video, you'll see the concentration of the EDTA solution that we used was 0.01 moles per litre. So we're going to start off with a 0.01 moles per litre of EDTA. And then we ask ourselves, did we use a litre of that solution? And we didn't use a litre of the solution. We used 3 different amounts on 3 different titrations. And my results that I got are here. So on my rough titration, on my first titration, I got 3.1 mils. That's my rough, so I'm kind of going to disregard it. Then my second titration, I got 2.9 mils, and in my third titration, I got 2.8. Now, because they're within 0.1 of a mil of each other, what I can do is get the average of those 2, and that will be my average titer. That'll be how much EDTA I used. So I add them up, divide by 2, and I get 2.85 mils. Now, I know how many moles of EDTA were in a litre. I need to know how many moles were in the 2.85 mils that I used. So I'm going to take the 0.01, I divide it by 1,000, and that gives me how much was in 1 single mil. And then I multiply that by 2.85, and that will tell me how much I had in my 2.85 mils. And it's 2.85 by 10 to the minus 5 moles in 2.85 mils of EDTA. So very, very small number. But now I want to convert that amount of EDTA into an amount of magnesium and calcium ions. So I'm going to need to use my ratio. So I go back up to my equation, and from before, my ratio is 1:1. So my ratio between EDTA and my metal 2+ ions is 1:1. I know how much EDTA I had. It was 2.85 by 10 to the minus 5 moles. So because it's a 1:1 reaction, there'll be the same number of moles of metal ions. But we need that in moles per litre. We know how much of the water sample we used. We used 100 mils at a time. So there were 2.85 by 10 to the minus 5 moles of metal ions in 100 mils of the water. So we have 2.85 by 10 to the minus 5 moles in 100 mils of my water sample, which contained the M2+. That's my M2+ ions. But we like moles per litre. So how am I going to get moles per 100 mils up to moles per litre? I'm just going to multiply it by 10. So if I multiply this by 10, I'll get 2.85 by 10 to the minus 4 moles per litre of my M2+ ions. And that's kind of like the first part of it done, because that's how many moles of the ions there were, but that's not an actual chemical that we could weigh out and stuff. We standardize this into calcium carbonate. We pretend that all of that calcium and the magnesium came from calcium carbonate. And the reason we're doing that is, if we look at the molecular mass of calcium carbonate, so calcium is a 40, carbon is a 12, and oxygen is 16, we have 3 of them, we add them up, we'll get 100. So it's a nice number to work with, so we just pretend it's all calcium carbonate. So I'm going to turn this into grams per litre of calcium carbonate now. Now to turn the moles per litre into grams per litre, we need to multiply by the molecular mass. So I'm going to take the 2.85 by 10 to the minus 4, and I'm going to multiply that by 100, this molecular mass, to turn it into grams. And when I multiply that by 100, I'll get 2.85 by 10 to the minus 2 grams per litre of calcium carbonate. If it was all calcium carbonate, this is how much will be dissolved in a litre, that many grams. But they're not the units we use when we're talking about water hardness. The units we use are parts per million of calcium carbonate. And what that means, parts per million, is milligrams per litre, but we have grams per litre. So the way we do that is we take our grams per litre and we multiply it by 1,000. So we're just going to have to multiply our grams per litre by 1,000. So we take this grams per litre value, and we're going to multiply it by 1,000, so 2.85 by 10 to the minus 2 times 1,000, and is that 28.5? 28.5, yeah. So it's 28.5 parts per million of calcium carbonate. And that there, this value, this parts per million of calcium carbonate, this is my total water hardness. That's my total water hardness. And again, what is total water hardness? It's the addition, it's the sum of our temporary plus our permanent water hardness. Permanent hardness. Okay, so that's not too bad of a calculation, but what has happened in previous exam papers when this has come up is they have said, okay, now you boil the solution and you redo the titration and you get smaller numbers. What's your concentration now and what does that mean? So if we think back to what boiling the solution does, it removes the temporary hardness. So if I boil the solution, I'm getting rid of the temporary hardness, and all I'm now finding is the permanent hardness. Okay? So let's say I redid this titration after boiling, and I found that my average value was, I don't know, 1. Let's just make up a number. It was a smaller value. And instead of getting 28.5 parts per million at the end, I ended up only getting, say, 20. So I ended up getting, after boiling, I had 20 parts per million of calcium carbonate. Now, because it was after boiling, the temporary hardness is gone. So this is just the permanent hardness. So that's the permanent hardness. So what do you think you would do then if you were asked to find the temporary hardness of that water sample? Well, sure, you know the total water hardness was 28.5. And you know 20 of that comes from the permanent hardness. So how much of it comes from the temporary hardness? We just subtract. So we'd take our 28.5 parts per million, take away our 20, and we'd get 8.5 parts per million calcium carbonate, and that would be our temporary hardness. So we can do it to start off with to find total hardness. Then we can go back to our water sample, we can boil it, and after we're done boiling it, redo the titration, and we'll get a value now for the permanent hardness because we've removed the temporary hardness. Now I know the permanent hardness value, I can find the temporary hardness value by subtracting from the total water hardness. Okay? So that is that titration finished as far as I know. So make sure to get this into your experiment books. I think it starts on page 99. And as you're going through this video, make sure you're looking at your green questions and make sure you're filling in the answers as they come up.